Activation functions are the secret sauce that gives neural networks their power. They decide whether a neuron should fire or stay silent, influencing how deep learning models learn complex patterns. In this video, I'll explore different activation functions, their importance, and when to use each. Let's dive in. An activation function is a mathematical function that transforms the input of a neuron into an output. Without activation functions, neural networks would be nothing more than linear regression models, unable to learn complex patterns. Activation functions introduce non-linearity, allowing neural networks to capture intricate relationships in data. Activation functions come in many forms, but we can broadly classify them into linear and non-linear types. Since deep learning requires non-linearity, let's focus on the most popular non-linear activation functions. First up, the sigmoid function. It squashes input values between 0 and 1, making it useful for probability-based predictions. It's widely used in binary classification problems. Pros include outputting values in a bounded range and working well in shallow networks. However, it's prone to the vanishing gradient problem, which slows down learning in deep networks, and it's computationally expensive. Next, the Tanh function. Similar to sigmoid but ranges from -1 to 1, making it zero-centered. This helps in faster learning compared to sigmoid. Pros are centered data, leading to better training efficiency and usefulness in recurrent neural networks. Cons include the vanishing gradient problem and computational expense. Then there's ReLU, the most widely used activation function in deep learning. It outputs 0 for negative values and passes positive values unchanged. Pros include faster computation and efficient training, and mitigation of the vanishing gradient problem. However, it can suffer from the dying ReLU problem, where neurons output 0 for all inputs and stop learning. Leaky ReLU solves this by allowing a small slope for negative inputs, preventing neurons from completely deactivating. Pros include avoiding zero gradients and working well in deep networks, but the small slope value is manually set and may not always be optimal. For multi-class classification, there's Softmax. It converts logits into probability distributions, ensuring the outputs sum to 1. Pros include ideal for multi-class classification and ensuring probabilistic interpretation of outputs. Cons are sensitivity to large input values, which can cause numerical instability. Finally, Swish, developed by Google, outperforms ReLU in some deep networks. Pros include smooth, non-monotonic behavior, allowing better information flow. Cons are its slightly higher computational expense than ReLU. So which activation function should you use? Here's a simple guide. Binary classification, use Sigmoid. Multi-class classification, use Softmax. Deep networks, use ReLU or Leaky ReLU. Recurrent neural networks, use Tanh. Want the latest tech? Try Swish. Researchers are constantly developing new activation functions that improve efficiency and learning performance. Keep an eye out for advancements in self-learned activation functions and adaptive activation mechanisms. To summarize, activation functions are the heart of neural networks, enabling them to model complex relationships in data. We covered why activation functions matter, the most common activation functions and their pros, cons, and how to choose the right activation function for your model. If you found this breakdown helpful, don't forget to like, share, and subscribe for more AI and deep learning content. Thanks for watching and see you in the next video.